Okay, good morning or afternoon. Thanks for joining this exciting webinar on the Trimble MX8 and mobile mapping with Geotrim. My name is Dana Brown. I'm with Trimble Geospatial Division, the land mobile sales responsible for North America. I will begin with the introduction and turn over to the Geotrim group to talk more about the exciting case studies on the MX8 and some of those applications. So today's agenda is to introduce you to Trimble Geospatial, introduce you to today's speakers, and then a discussion about Geotrim, their particular system, and some of the projects that they've done quite successfully with the MX8 system. And then we'll wrap up with a Q&A. So the Trimble MX8 comes from the Geospatial division, another exciting division within Trimble. Within that division, there are workflow solutions both from the land and from aerial. Today's focus really is that upper portion of the land, which is the MX8 and Trimble Trident Analyst, the software that completes that workflow to that end deliverable. So for today's speakers, we're going to have two that have joined us to present this. The first is Mika Customo. Mika Customo is a land survey engineer. He graduated in 2006 with a bachelor's degree of engineering. During his studies, he specialized in measuring techniques and geographic information systems. Currently, he works as a sales engineer for mobile mapping, survey, and infrastructure monitoring solutions at Geotrim. His areas of specialty include mobile mapping, aerial photogrammetry, airborne LiDAR, field surveying, GNSS and IMU calculations, UAS, terrestrial laser scanning, and infrastructure monitoring. The other person joining on this presentation is Anna Clements. So a year ago, Anna began working for Geotrim when the MX8 was acquired. She came to Geotrim straight from a university where she's still a student, studying geomatics with photogrammetry as a major. Currently, she's writing her master's thesis about the mobile mapping process with the MX8. Part of her thesis is to create a 3D city model from MX8 data. She hopes to finish her Master's of Science degree by the end of this summer. At Geotrim, she is the technical specialist and the operator of the MX8 and processing the collected data. She is responsible for all mobile mapping activities at Geotrim. So with this, I will turn it over to Mika to discuss the details about Geotrim and those projects.
Thank you, Dana. On Geotrim's behalf, I would also welcome you everyone to listen to this webinar about our Trimble MX mobile mapping system and as well as the projects that we have done with it this year. I hope that you maybe learn something new about mobile mapping and you find the two project cases interesting. As Dana already introduced me, my name is Mika Customo and I work at Geotrim as a sales engineer, and I will be presenting today this webinar together with my colleague Anna Clements. As we are aware that mobile mapping might be something new for some of you listening, we try to keep the presentation on a more general level, and if some of you want to know more details on the topic, we are happy to answer those questions in the Q&A session at the end of this presentation. In this webinar, I will present a general overview of our mobile mapping operations and tell you a bit more about what Geotrim is. Anna will present the two project cases as she was working on the field on both of the projects. Who are we, or what is Geotrim? Geotrim is a Trimble dealer and a certified service partner for survey, heavy and highway, and construction products in Finland. Currently, we have 31 employees who all have experience in service, surveying or maintenance of surveying instruments. Mobile mapping has been part of our operations since last year, 2011, and so far we have completed about 20 projects with it. Our office is in Vantaa, and we also use the same office as a base for our mobile mapping operations. Why mobile mapping? The main reason for this is that we see mobile mapping as a new and promising business field with high expectations in the future. In our domestic market, there has been already projects completed for a couple of years with mobile mapping, and there has been a demand for more easy access to this equipment. As a surveying technique, mobile mapping fits perfectly between traditional surveying on the field, total stations and satellite measuring, and the airborne surveying techniques like aerial photogrammetry and airborne LiDAR. It also offers cost benefits in medium-sized projects that require higher accuracies. Having our own mobile mapping system, we have been able to serve our customers in Finland and Europe so that they have easier access and faster process through the whole mapping project. In Trimble MX8 mobile mapping system, we saw an opportunity to invest in the latest mobile mapping technology and also an opportunity to develop the mobile mapping industry in Finland. MX8 also included some features that made the post-processing of the mobile mapping data a lot easier. And we saw things like integrated scanners and cameras in the mapping unit, and also time synchronizing and option to shut down the scanning during the stops, tools or options that made the whole post-processing part of the operations easier. Our system, the mobile mapping system, consists of two main components. First one is the Trimble MX8 mobile mapping system, shown the picture on the top of our mobile mapping vehicle. The second part is the Mercedes-Benz Viano 4x4 minibus that we use as the main platform for our mobile mapping system. In this setup we have used a standard minibus with no modifications, which means that the whole system is also very easy to transfer to other mobile mapping platforms. For example, if we need to take it off from our vehicle and set up to our customer's vehicle. With our vehicle, we have chosen to use two-persons operations for the system. For this, there are two main reasons. The first one is safety, and the second one is quality control. In our setup, the driver can fully concentrate on the traffic and drive optimization for the mobile mapping. This way, we can operate the system safely and without reducing the quality for the mobile mapping. At the same time, the MX8 operator has a full control over the mapping system and can do the real-time quality control for the mapping. This means that during the mobile mapping, the quality of the laser scanning, the positioning accuracy, and the image quality of the digital images can be already seen during the acquisition. This means that there are no surprises in the final processing of the data. On our experience, this has also reduced the amount of reruns we had to do, or in smaller projects it has had cost effect on the projects itself. Our Trimble MX8 has multiple sensors, and the core of the system is the mapping unit shown on this slide on the right side of the slide, and also on the top of the car on the left top corner of the slide. This unit has two VQ laser scanners, both of them 360-degree laser scanners, and which are set in a butterfly configuration, so we can scan when we pass objects on the road. We can scan around the smaller objects. The digital camera system has two parts: the forward-pointing panoramic camera system that gives us 170 degree on the front of the mapping unit, and also backward and downwards pointing road surface camera on the back of the mapping unit. This will give us more detail about the ground conditions, the road conditions, or the surface that the mapping vehicle is driving on. The positioning of the mapping unit is handled by a Aplanix Boss LV520. GNS has an inertial system, and it also has a digital distance measuring unit set on the left back wheel of the vehicle. With this, we get the accurate positions, the satellite data and the inertial data recorded for the post-processing. This is also the core of the accuracy of the whole data that we collect with the mobile mapping. The multiplexer synchronizing system in the Trimble MX handles all the sensors and the positioning information so that all of them have exactly the same timestamp. And this is very important when you start processing and combining multiple sensors to the track of the vehicle. The data acquisition with the MX8, the data we collect, there's two types of data. The 3D laser point cloud that comes from the two VQ250 laser scanners. We can collect up to 600 points per second, but usually this collection rate and also the scan rate for the lasers is adjusted so it fits better on the specific project specifications. This means that it's not always the best option to have everything collected at the full rate. We also acquire digital images. We could collect up to 48 images per second, but as with the laser scanning, we usually adjust the image interval so that we get image, for example, in city environment by 2 or 3 meters, every 2 or 3 meters, and on the highways 10 meters is usually a very good option for the image collection. This way we can also avoid the effect that we have many images, overlapping images in a small area. On the images on the right you can see the point cloud. The result, this is a bridge we draw here in Finland, and that's the point cloud that was collected from the mobile mapping. And on the bottom right you see another picture which has the front camera, the digital image taken, and that's overlaid on top of the point cloud in the Trimble Trident software. So we can see the same things from the image and maybe getting more information what was in the image and in the point cloud. What is the benefit of getting a 3D laser point cloud and digital images of the same area at the same time? If we would only have laser point cloud, we would have a lot of millions of measurements with X, Y, Z coordinates, each of these points presenting an accurate position, but not necessarily containing all the information what was actually measured. With digital images, we get a very nice view around the vehicle, and we can see mapping objects, areas of interest from the images. When we combine these two, we get the benefits out of both techniques. With the 3D laser point cloud, we get accurate measurements, and when we add the images on top of these, we will get also information what was behind each individual measured point, and also, more important, what was between those 2 points. And as you can see from this example, also things that you see on the images, for example, from the road surface or the materials on the bridge rails, those kind of things are very hard to identify just from the point cloud. But when you have the point cloud and the images, you can very clearly say that, okay, there's small cracks on the surface of the road. So, as said in the start, we have 2 case projects in this webinar, and after I will introduce shortly to the 2 case projects, Anna will continue and tell you more details about those. The case project, the first project, Road 51, was done in Finland. The first project, it was a road construction project that we did this spring in Finland. There was a very high accuracy requirement in the project. We found this project very interesting because it really showed the capabilities of mobile mapping and how it can reduce the cost of such projects in the future. The second project, the vehicle testing track in UK, that was an off-road track mapping project with multi-use plans for the actual data. During this project we did push our 4x4 minibus to the limits. That said, I will now let Anna to tell you more about the project itself.
Thank you, Mika. So as said earlier, my name is Anna Klemets and I'm the technical specialist when it comes to the MX8 and mobile mapping at Geotrim. On both of these projects that we are going to present to you, I was the operator of the MX8 and I also did the first stages of the data processing on both of them. As Mika said, the first one is a highway project and it was done here in Finland in Kirkkonummi, which you can see as a red mark on the map on this slide. We want to share this project with you since it really represents Trimble and what Trimble stands for. By that I mean the aim to provide users with technology for the whole workflow of a project. The main contractor in this project was Destia, and the 3D milling was carried out by NCC Roads. Both of these companies are very future-oriented companies. First, I'm gonna explain to you the purpose of this project and why mobile mapping was used. Then we are going to go deeper into what was done in the project and how it was done. The project was part of a research project here in Finland called InfraFin BIM. The purpose of InfraFin BIM is to develop the process of data model-based road network management and maintenance. The aim is that by 2014, all major companies in the infrastructure business will require BIM model-based services. Part of this project was also to investigate the suitability of mobile mapping as a way of collecting accurate data for the data models. This was also a pilot project for using mobile mapping data in a Trimble Machine Control system. The purpose of the construction was to make a 2-lane road into a 4-lane highway, and the old road would become the 2 lanes going in one direction. In road geometry, this means reconstructing the crown of the road and doing this with 3D milling to make the construction as effective and as economical as possible. For this to be possible, the mobile mapping needed to be very accurate. The absolute accuracy needed to be on survey level. Also, the schedule for the project was very tight, so the mobile mapping needed to be done as soon as possible. Here you can see the whole time frame for the project. The offer for the mobile mapping was accepted on the 24th of April, and the painting of the reference points started on the 25th. When the reference points were painted, the mobile mapping could be carried out, and this happened on the 26th of April. Some of the reference points were not measured by then, so the measuring continued on the 27th. The georeference point cloud and images, they were delivered to the client on the 2nd of May, and then by the end of May, the road planning and the machine control models were completed. And so on the 7th of June, the 3D milling started, and it was completed in 2 days. So this means that the whole project was done in about 6 weeks, which is very good, especially since it was a pilot project and some of the stages included training. To give you a better understanding of the different stages in the process, I'm now going to go through the workflow of the whole project, and then later on I will focus more on the mobile mapping and the 3D milling, and of course the results that we achieved. So the first stage was to do the mobile mapping, and this was done with the MX8 using the Trimble Trident Analyst software. After pre-processing, the further processing of the mobile data was done in TerraSolid software. The processed point cloud was then transferred to Tekla Civil for the creation of the terrain model and the alignment design and the optimization. The design was then moved to Trimble Business Center for export into the right format for the Trimble milling grade control system. And finally, the 3D milling, which means removal of old pavement, was done with a Virgin W2100 using the Trimble Machine Control system. Now that you have an idea about the project as a whole, I'm going to go more into details regarding the mobile mapping part of the project. The mobile mapping was done for the creation of the machine control plan, so what was done in the project was based on the collected mobile data. And due to the accuracy requirements, reference points were created on the whole project area 200 meters apart on both sides of the road. Points were put as close as possible to the track of the vehicle. And these points were measured by the client. In the image in the middle, you can see the target that was used for the reference points. The important thing is that it's possible to precisely extract the measured reference points using the target. So that means that the target needs to be big enough to show in the point cloud. And reference points are used to increase the absolute accuracy of the data. As for the actual mapping, it was done at full rate, which means that the scanners measured 300,000 points per second. The system was set to record the last echo of the laser beam, and the cameras were set to take one image per 5 meters. And all of this was done at about 40 kilometers per hour to get good coverage. And in the image on the left, you can see an image of the road taken by the backward pavement camera. And on the right, you can see the point cloud. Also, in these images, you can see the target used for the reference points. And as I said, the processed point cloud was then used to create the models for the machine control system. So the results from the mobile mapping you can see in these pictures. These are the plans for the 3D milling. On the left, we have an overview of the project area, including the masses to mill or to add. The areas needed to mill are painted in blue, and the areas that need more pavement are painted in red. The same coloring is used in the image on the right, which is a detailed plan for the milling. The yellow color here means that the level of pavement is good. So these plans were then transferred to the machine control system, which you can see in this slide. In the middle, you have the milling machine, and around it you can see the Trimble Machine Control system parts and where they were placed on the machinery. As you can see, the package includes a Trimble electromagnetic UTS total station, and this provides the coordinates for the machine control. The machine control system comes as a package, and it's very easy to install. It takes about half a day, plug and play principle. And from experience, we can say that the accuracy of the milling is plus minus 5 millimeters. Here you can see the 3D milling in action. So 3D milling means that the hydraulics of the milling is controlled by a machine control system, which in this case was a Trimble GCS 900. And the machine control system follows the plan created with the MX8 data. On the right, we have the machinery, and on the bottom image, you can see how much old pavement needed to be removed on some places. And on the left, we have an image of the result. The 0 painted in red means that the amount of old pavement that was removed was the accurate amount, and the +2 means that 2 millimeters too much of pavement was removed. And these values were then measured with a Trimble total station. Overall, the whole project was a big success. The client was very happy with the results, and the mobile mapping gave a new, effective and accurate enough method for collecting data for the data models and for road planning. This is a new and very effective way to do 3D milling, and also, if I might say so, the right way to do it. The safety benefits of doing mobile mapping compared to traditional survey methods were very important to the client. By safety benefits, I mean the fact that the surveyors in mobile mapping are moved from amongst the traffic to inside the safe walls of a van. Okay, now I will move on to the next project that we want to present to you. So we now go from Finland to the UK, and from one mobile mapping application to a totally different one. The reason that we want to present this project to you is that it is a very different application for mobile mapping, and it proves the versatility of mobile mapping. The object in this project was vehicle test tracks, and it was done in cooperation with Corec Group. And the idea was to map vehicle test tracks with the MX8. The whole project had three major purposes. The first one being feature extraction to support ongoing research. The second one was to document the test tracks while it's still possible, because some of the test tracks are now being used for something else than testing vehicles, or the areas are being replanned. The third purpose of the mobile mapping of these test tracks was to get data for creation of virtual test tracks. So in the future, the client wants to do the testing of the vehicles in a simulator instead of actually testing the vehicles on a test track. The requirements in this project was to find an effective way to gather detailed data about the test tracks. Effective in a way that as many tracks could be mapped as fast as possible, but also effective in the sense of coverage and collecting different kind of data. In this project, the relative accuracy of the data was the main criteria. And so we had 2 weeks in March to map as many test tracks as possible, and we ended up doing 7 sites. In total, this was about 150 kilometers of test track, which means about 1.5 terabytes of raw data. Most of the processing was also done during these 2 weeks, and the final version of the processed data was delivered to the client by the end of May. At all the sites, images and point clouds were collected. In the images below, you can see examples of the collected data. On the left, the point cloud, and on the right, the imagery. And in the middle, you can see the trajectory of the covered area, which also was very important to the client due to the nature of the purpose of the project. By trajectory, I mean the GPS track for the position of the mapping unit. Also, in this project, the data collection was done at full rate, but images were taken every 3 meters. And the mapping speed was at a maximum 30 kilometers per hour. These test tracks consisted of off-road tracks, obstacle courses, and alpine courses. And as you can imagine, this is not a very friendly environment for mobile mapping, and certainly not for a Mercedes-Benz Viano, but I must say it did surprisingly well. So the delivered data was a georeferenced point cloud and images of all the sites, and as you can see in the example images, a very detailed point cloud with good coverage to support the point cloud images of the same area. The 2 bottom images to the right are from the same area, one snapshot of the point cloud and the matching image to go with the point cloud. With this high quality data, it's possible to make a virtual test track for the simulation that is actually very comparable to the reality. And with a dense point cloud like this, it is possible to extract very small details of the track. For example, the stones in the obstacle courses you can see here, especially when you have images to support the point cloud. And if you look closely on the point cloud, you can see that there is minimum, if not none, noise in the point cloud. And on the right, you can see images from the alpine course And as you can see, the track is very steep. This also gives a better image of what the test tracks looks like. The client was very happy and satisfied with the result, and he is now starting to make use of all the data. The client was also surprised on how detailed the point cloud is. So I have now presented to you two very different projects, but they show the versatility of mobile mapping and that there are very unexpected applications for this technology. They also very well show the effectivity of the MX8 and the high quality one can expect when using the Trimble MX8. So as a conclusion, we have gotten very positive feedback on all our projects from the client regarding the effectivity of mobile mapping with the MX8 and also regarding the accuracies of the data. And comparing mobile mapping to traditional methods, this has proven to save time and also money. Further, also the safety factor has been a very important benefit to a lot of our clients. As for the future of mobile mapping in Finland, the trend is very positive, especially as the knowledge about the possibilities in mobile mapping is spreading. And I can tell you that my calendar is filling up with mobile mapping projects for this summer. We have also been surprised with the fact that clients come to us with new applications for mobile mapping, especially clients that have areas that need to be mapped that have been challenging for traditional methods. So you could say that the clients have been very active in this sense. Okay, we want to thank you for listening, and we are happy to answer any questions that you may have.
Okay, thank you, Anna. My name is Brian Stoss. I'm a marketing associate with Trimble Geospatial. At this time, we will accept any questions that you have. First question comes from Frank, and he was wondering why you would use the car tires to measure distance. Curious if that is an accurate method.
Okay, the distance measured on the car tire, that was on the slide 7, showing the vehicle. It's only used in areas where you can't use GPS for some reason. For example, if we drive to a tunnel, we need to use the DMI to define the actual speed of the vehicle as well as the distance traveled inside the tunnel or other area with GPS obstruction. So with that we can improve the accuracy in areas of no GPS coverage. And otherwise we of course use the GPS and the usual systems in the MX8 because those are the most accurate parts of the system.
Okay, thank you. Another question, which should be pretty easy, which LAS format does the MX8 use?
The MX8 uses internally LAS format 2.0, but usually in Finland we use, our clients use LAS format 1.1 and 1.2, so we generally transform the files to the older versions of LAS format.
This question might be for Dana. Someone's wondering if we have marketed or sold the MX8 for use with overhead power lines, I believe is what they're asking, if the MX8 is able to measure those.
Yes, we have some of our clients using MX8 for overhead line applications. And if they want to contact me later time, we can share more details.
Okay. Another question is why you chose to install the MX8 on the vehicle that you chose. What was your reasoning behind that?
Okay, there are a couple of reasonings on that. Of course, Mercedes-Benz Vienna offers a nice room inside the vehicle, so we have room to operate. Then also it's a standard vehicle, so we don't need any special modifications. And in case if we need to move it to other platform, for example in Project Abroad, we can just open a couple of bolts inside the vehicle and On top we have the ski racks, and we open the locks on those, and the whole system is removed from the vehicle in 30 minutes. And as said, we didn't need to modify the vehicle to fit anything inside it, so that was the main reason.
Okay, I think we'll do just a couple more questions, so if anybody else has any more, please get those in, and we'll wrap it up. The next question is, someone's wondering what the scanning range is for the laser scanners.
Okay, with DQ250 laser scanners, we can get reflections from up to 500 meters from objects, but I would say typically in the road environment, it's very, very rare case that you can see something over 100 meters from the road. In city environments, we usually get something from 50 to 100 meters from the road, and of course in the highway we might get a bit better distances, and also because we set the system quite high, so about 3 meters, so we are not obstructed by everything that is very low next to the road, so we get quite good distances.
Okay, great. The last question we'll do today is what is the size of the target that was used as a reference point? I believe this was on the side of the road there.
I can answer that. The target that we used was two 20 centimeter by 20 centimeter squares. So in total, the size of the target was a bit over 40 centimeters.
I would also add to Anna's answer that the size of the target basically depends on how fast you collect the data. So if we drive at 80 kilometers per hour, which is roughly 50 miles per hour, then we need bigger targets because otherwise they don't show in the laser data. But with city speeds, that 20 by 20 centimeters is big enough.
Okay. We actually had a couple of really good questions come in here at the end. If we could just go through them. Someone wants to know how the system accounts for the vehicle sliding back while trying to climb some of the rugged road in that project you guys showed.
So you will get, since for example, the images are set using the distance measured by the DMI, you will get, if you are sliding or the wheels are turning faster, you will get more images. So I wouldn't say that it's a part of the system that it accounts for the vehicle sliding backwards, but we didn't recognize any problems even if we have at some point had the vehicle sliding.
Okay, great. And this will be the last question. Matt wants to know if you used any target points in the second project. And I guess if you did or you didn't, what was the reasoning behind that?
We didn't use any reference targets just because of the fact that the requirements didn't, according to the requirements, we didn't need any targets. And also another reason was that acquisition needed to be done fast. And the third reason is that it's also, if you have a project and you realize afterwards that the absolute accuracy is not good enough, you can always go out back to the area, find features in the point cloud that you can easily find in the field, and you go and measure one of those or distribute reference points over the area and measure them afterwards, and also do the registration of the point cloud afterwards.
Okay, great. Thank you all for attending. Thanks to our speakers today. If anyone has any more questions that we didn't get to, some of them we'll try to answer offline. If you think of any other questions, you can go ahead and either send us an email at Trimble or Mika or Anna an email at Geotrim using the email addresses on your screen. Thank you very much for attending, and we hope that you will join us for the next webinar.